Okay, so I'm going to use this that we had derived before, right? The average energy, we're going to use this again for some of the other derivations. Okay. Photoelectric effect. Let me see. We've been doing the heat capacity. So the photoelectric effect, if you remember, our idea previously was light shines on it. According to classical mechanics, the light shines on it, it should build up energy and eventually kick off an electron, right? Because light is a wave, it doesn't come in particle fashion. But Einstein used Planck's hypothesis to suggest that the energy being emitted isn't just a wave, but also comes in packets. And he called those packets quanta, right? Now, Planck, when he was saying E is equal to h nu, he was just using it as a mathematical way of deriving the equation that he wanted. So it was a mathematical shortcut. At that point, there was no physical meaning to it. It's just the math works out, yay, let's use the math. Einstein developed a theory based on that equation working out. So what he said is, they're coming in packets. And so if it's coming as a packet, you can think of it as a particle holding that packet of energy. It's not a wave that can have any sort of wavelength. They have a packet, and so they come in chunks. So if the light is coming in chunks, if we take a look at the photoelectric effect to see what that means, because electromagnetic radiation is coming in small packets called photons, where each energy is equal to h nu, he ended up showing that the kinetic energy, which is 1/2 mv squared, is equal to h nu minus some threshold value. So if we think about what's going on with the photoelectric effect in terms of our new view of light coming in as individual packets, and you can imagine an atom absorbing one of those packets, the packet comes in, hits the atom, it's either absorbed or it's not. And when that packet hits, if the atom absorbs the energy, it starts moving and then can flush the energy out to the rest of the molecule. So if you don't hit it with a high enough energy packet, that energy starts to dissipate. So it explains why if you put IR light, shining it onto a surface, the surface will heat up, but it won't be kicking off electrons, right? So the individual packet comes in, hits that metal molecule, it absorbs the energy, and then through vibrational modes, spreads the energy to the rest of the metal. If, however, that photon of light hits the metal and it has enough energy to kick off the electron, it kicks off one electron. One photon hits one metal atom, kicks off one electron, right? Which is why as you increase the intensity, more photons are coming in, more electrons are coming out. In terms of the energy of the electrons coming off, there's a certain threshold to pull the electron out. Once you meet that, any additional energy gets put into the electron moving at a faster and faster speed. So this threshold energy is called the work function. It's essentially just the amount of energy that it takes to pull the electron off. Any additional energy, so this would be the amount of energy of the photon minus the energy holding the electron in, is how fast that electron's coming off. Right, so the kinetic energy that's being imparted onto the electron is the amount of energy to rip the electron away, plus any extra energy gets converted into kinetic energy, which actually agrees with what we see, right? If you hit it with a shorter wavelength of light, the electron comes off faster. And the reason it comes off faster is you put enough energy to pull the electron off, all that extra energy goes into kinetic, right? So that ends up agreeing with here, we have a certain threshold. Below that value, no electron comes off. if you give more energy, so this is increasing the frequency of the radiation or decreasing the wavelength, i.e. giving you higher energy photon, the electron coming off has an increasing amount of kinetic energy. Right? It scales linearly with the energy of the photon. So the more energy of the photon, the more energy of the kinetic energy of that electron coming off. Right? So it is completely consistent with the idea of the energy coming in as packets, coming in contact with that metal center, ripping off one electron, and that electron coming off with the excess energy. Right? So this idea, or this theory that energy is, or the light comes in as a packet of energy, a single packet hits a single atom, kicks off a single electron, is consistent with all the experimental evidence for the photoelectric effect. Right? If that photon of light doesn't have enough energy, electron's not going to come off no matter how many of those photons are coming in. You have to first, in that initial instant, give it enough energy to pull the electron off. If you don't, the energy gets dispersed and doesn't kick off any electrons. So no matter how long you shine IR light onto a metal surface, electrons will never come off. The metal's going to heat up, which it does, but no electrons ever come off. You have to hit it with the right wavelength of light so that that one photon hits that one metal center and kicks off that one electron. Does that make sense? Yeah, so that is again showing that we have this idea of quantization, that light is behaving as a particle and not always as a wave. So it's coming in with a certain amount of energy. That particle of light is holding a certain amount of energy, hits the metal center, kicks off an electron. Right? So this is giving further credence to the concept that light has both wave and particle nature. This is one of the big things, or the big pieces of experimental evidence that led to the wave-particle duality of light. Is this does not work if light is just behaving as a wave. It only works if one photon hits one metal atom, kicks off one electron. Right? A wave wouldn't work like that. Okay, so this is giving sort of evidence for wave-particle duality. And this is what led to Einstein's Nobel Prize in, I want to say the 20s? 20s or the 30s? I should know that. Okay, so Einstein didn't actually win his Nobel Prize for relativity. Probably should have, but given the biases against Jews back in that period of time, that's why it actually took decades for him to be awarded the Nobel Prize for this, which changed physics. Germany was big into science, and they had a lot of say in Nobel Prizes, and you know what happened. Yeah, so probably should have gotten two, one for relatively and one for the photoelectric effect, but he still won one, which isn't too shabby.
What happens to the metal? What happens to the metal that the light is hitting? Since it's losing electrons,
it becomes charged. Yeah. So the fix is conceptually the photon has a certain amount of energy. Photon hits, kicks off an electron, and it will only kick off the electron if the photon has sufficient energy to rip the electron away from the metal center. So one photon equals one electron removed. The extra energy beyond the work function is converted into kinetic energy. So if we go back to this, what we can do, and this goes back to those learning objectives, right? So the type of thing that you would see on a test is we have this equation where the kinetic energy is equal to 1/2 mv squared, which is equal to h nu, the light, minus the work function. So you essentially have, so this is frequency, that's velocity. So they look the same, but they're, unfortunately they look the same, but they're different. So I guess this one here, more of a V for velocity. So you have 5 different variables. Well, 4 variables, that's a constant, right? So I could give you 3 of the 4 and ask you for the 4th, right? Or say, this is the work function. Yeah, I'd give you work function. What's the velocity of an electron coming off? And then in some table, the mass of an electron, right? You know, so light at a particular frequency hits a metal surface. That metal has a work function of a particular number of, I don't know, kilojoules per mole or electron volts. What's the velocity of the electron that gets kicked off, right? So that's sort of the thing that you're going to see. One of those will be on the homework, 1 or more for you guys to practice. And that's sort of one of the types of things you might end up seeing. Okay? Probably don't want to be on the next slide. Okay. Heat capacity. Okay. So, Albert Einstein used Planck's idea. Actually, probably should have gotten a Nobel for this one too. But used Planck's idea of quantized energy and applied it to oscillations of atoms. So previous to this point, the idea of quantization had only really been applied to realistically photons, right? So we're thinking, okay, photons are these weird things. They can be quantized, but nothing else, right? What Einstein did was he said, okay, well, let's apply it to atoms. Let's see what that does. So this is the first application of quantum mechanics to non-photons. So he's applying it to atoms as well. Well, photons or electrons being quantized. So you can view atoms, so a conceptual model for developing your mathematical equations that was used by DeLong Petit. So this was the original, if you go back a couple slides, this is the original heat capacity where it should be 3R. DeLong. Was where the heat capacity was equal to 3R. Okay, so the way that they constructed this view is using the idea of chemical bonds being springs, right? At this point they know that you have vibrational modes, and you can think about the bond as being a forced spring, and then the 2 atoms are weights on the ends of the springs. So this is how they were viewing the world to make sense of their equation. So let's say you have atom A, spring, atom, I'm going to make that bigger. Yeah, it's going to make it a lot bigger. Okay. Okay, so if you're thinking about a crystal structure, right, or a metal surface that you're shining light on and heating up, or I guess you don't have to be shining light on it, just a metal surface that you're heating up. We're going to start by just picturing them in a line, and then imagine them a better drawing in sort of a 3-dimensional lattice, right? So moving just along the x-axis, you have your atom, conceptually a spring between it, another atom spring, another atom spring. You can view it as basically a whole bunch of balls that are held in a 3-dimensional lattice with springs between them. So you can take a ball and you move it away from one, and so that's going to compress one spring and extend another spring. Okay? So let's look at, as these things vibrate, right? So I'm making B move away from A towards C. Right, and I'm keeping C and D. Essentially, I'm keeping A, C, and D in the same location, and then I'm just moving B along the x direction. So if B is moving in this direction, it is building up potential energy. That is equal to sort of the kinetic energy that it's absorbing. So that would be 1/2 kBT, right? That's, if you go back to when we're talking about energy and temperature, when we were using classical mechanics, Newtonian physics, right? We said that energy was kBT. So going in this direction, you get 1/2 kBT. You're also extending it by 1/2 kBT for your kinetic energy, comma. So your total energy along the x direction would be equal, this is along the x, so this would be equal to the kinetic energy along the x plus the potential energy along the x, right? The total energy is equal to the amount that's being stored in potential and the amount of energy in motion, right? So along the x direction, this would end up being, for each motion, the kinetic energy is storing 1/2 kBT and the potential is 1/2 kBT. This is along the x direction. We can imagine the y and the z direction, so that's just going to be 3 times that amount, right? The energy that's stored in the x, the y and the z should be the same because the atoms don't know directionality. So the energy total will be equal to 3 times the kinetic energy we found for the x direction because we got the x, y, and z, plus 3 times the potential energy that we just figured out for the x because you got potential energy building in the x, y, and the z. Okay, so that is equal to 3/2 kBT plus 3/2 kBT, or 3 kBT. Now this is per atom. Our ideal gas constant is equal to Avogadro's number times Boltzmann's constant. That's how the two are related. One is on the mole scale, and the other one's on the atomic scale. They're the same thing, just different scales. So if instead of talking about the total energy for an individual atom, or total, yes.
On the big one, right? You said total energy is x, y, and z, right?
Yep.
So 3 kex, which accounts for all the directionality for
X,
the
Y, and Z.
energy.
Yeah.
And then potential energy x, y, z, which is 3 times the x energy.
Mm-hmm.
But how'd you get 3/2?
Each one is a half.
Oh, I'm sorry.
And then we got 3 of them. Yep. So 3 sets of 1/2 gets you the 3/2 for each. So that gets us a total of 3. So if we scale this up to on the mole scale, then this would be the energy total is equal to 3R times T. Now, E, energy total, if you're looking in a lot of physical chemistry books, one of the more frustrating parts, and I'm trying to minimize the amount of this, but so that if you're looking at other locations, you know what you're seeing. Energy is a lot of times represented by a U, right? So that's the total internal energy. They use U for that a lot of the time. So U is equal to 3RT. If we're looking at the U, dt, we're essentially taking this equation, taking the derivative of that with respect to t, which would just be 3r, which is the Dulong-Petit law. Right? This is how they came up with that. It should be 3r, this is their conceptual model. These are how the forces work out, and then when you scale it up, it should come out to be 3r. And heat capacity is that when you're holding volume constant.
What is R equals N something kb?
Na, Avogadro's number, times Boltzmann's constant. Boltzmann's constant is essentially the ideal gas law at the atomic scale. Right, so R has units of joules per mole Kelvin. Planck's constant is joules per atom Kelvin, essentially. Okay, so this is according to classical physics. But what they found is that as t goes to 0, the heat capacity goes to 0. This in no way explains that if this is your energy, t can go to 0 just fine. Right? T goes to 0, the derivative stays the derivative. Right? T is nowhere in here. Right? So as t goes to 0, this thing should stay constant. So if we now apply, instead of this being how energy is stored, if we say that the total energy is using this, right, quantize it, as opposed to using, so instead of using Newtonian, the kBT, instead of using Newtonian value for energy, if we use this quantized value and look to see how that plays out. So essentially, instead of having 3 kBT here, we have 3 times that. It's using the exact same thing, except instead of kBT, we just plug in our other value for energy as that. So we would get, that's classic. Our energy total, which again is U, would be 3 times Avogadro's number. So 3 times our Avogadro's number times, so instead of kBT, we're using that. So times H nu over E H nu kBT minus 1. Okay, so our heat capacity, CV, is equal, technically it's the partial derivative. Have you guys seen partial derivative? It's essentially the exact same thing as a derivative, right? The reason that it's a squiggly D is we're saying treat everything else as a constant, other than the variable that you're working with, right? But it's not, because the function depends on multiple different equations, so this is a symbol that's used for multivariate as opposed to single variate calculus. The way that you approach it in terms of taking a derivative, it's the exact same thing, right? But like volume can have an effect on certain parameters, right? So in this case, we're treating the volume as being a constant and then taking the derivative with respect to temperature. So because we're holding some stuff constant, it's actually the heat capacity itself, and if you take 401, we go into how this one varies with pressure, volume, temperature, and all those other factors. So we're saying volume is being held constant. How do things get affected by heating up? Or putting a little bit of extra temperature, how much energy does that take? So we're taking the derivative of this equation here with respect to temperature. So the top part is a constant. Unfortunately, we got this thing down at the bottom, an equation within an equation within an equation. Right, so we're gonna have to use the product and chain rules. Right, so just a reminder, the product rule is if you have two functions, let's say f of x times g of x, you want to take the derivative of that, that is equal to the derivative of the first times the second plus the first times the derivative of the second. And because they're added together, some people say the first times the derivative of the second plus the derivative of the first times the second. You'll hear it in either way, you know, it doesn't matter. Right? The chain rule is if you have a function embedded in a function. So let's say d of f of g of x. All right, so this is some function embedded within a function. This would be the derivative of the outside with the inside still being as it is times the derivative of the inside. Right, so those are the products of the chain rules. You can see here we have we're going to be taking this with respect to the temperature. This part here can be thought of as a function embedded within e raised to a function, embedded in a 1 over, or you could, so it's a function embedded within a function. If you work it out using the product and chain rule, what we find is that this is 3NA KB, the KB comes from down here, H nu over KBT raised to the second power E H nu over KBT divided by E H nu KBT minus 1 squared. Okay, now, this part here, NAKB, that's R. Right, so we can move this back to being on the molar scale. We can simplify this and replace this part here with R. Right? So that's equal to 3R times okay, the reason I did that is to emphasize the R part, right? So, the DeLong Petit law works really well at high temperatures, right? You'll find that things typically follow, you know, this heat capacity CV, the molar heat capacity at room temperature for most things, and then at high temperature for just about everything, except, you know, water's a weird one. But for most things, particularly metals, follows this 3R just fine. So experimentally, this here works really well for most things at room temperature and higher, right? Where it fails is when you start getting to lower temperatures. So as our temperature creeps up, as T goes up, we should get back 3R. Right? That's the value that we should end up getting. So as T or goes to infinity, right? As T gets big, this thing should work out. So as T gets big, let's see what happens. T here gets big. This part here goes to 0. That goes to 1.
The 1 is the top one.
Drop it.
Because if you differentiate -1, it should go to 0. Not related to 0.
We use our same expansion that we did before. Yeah. We can use that same expansion that we did with our E before. So this should approximate. So before we were looking at 1 over wavelength, so the X was on the bottom. We're now looking at how temperature is. So we end up with the same situation where we're really looking for the limit as E to the 1 over X as X goes to 0. This would go towards infinity, i.e. this term gets bigger than that term really fast. So this -1 becomes insignificant. So let's start with limit as T goes to 0. This becomes 3R H nu Okay, so I just added those parentheses right here. Carolyn? I just added a set of parentheses here. You got them? Okay. Yeah, I do make mistakes, but try to catch them. Okay, so as X goes to 0, this the -1 becomes insignificant. So we're going to drop that term, so we get E to the H nu kBT over essentially E to the H nu kBT squared. Right? This term here will cancel out that term there. And so that gives us 3R H nu over kBT squared over E H nu ABT. Okay. So as T goes to 0, we're looking at this. This is E raised to what's going to end up being infinity, right? Over 1 over, so this part here would be infinity. So the question is, does this infinity go to infinity faster than the bottom infinity does? All right, so this is 1 over 0 raised to the second power. Does that get big faster than E raised to the 1 over 0? The E raised to the 1 over 0 goes faster. And so this whole thing goes to 0, which is what they saw experimentally, right? As temperature goes to 0, heat capacity goes to 0. So this ends up equaling 0, which agrees with experimental results. Okay, so what about the limit as t goes to infinity? Okay. So as it goes to infinity, this part here goes to 1.
There's the one period problem.
Oh, no, sorry. From before, as this went to infinity, and if you look back at your notes, we had, as this goes to infinity, this goes to 1 plus 1 over x. There we go. That's what it was. Okay. So this becomes 3r times h nu over kBT squared 1 plus 1 over x, so this would be kBT on top, h nu on bottom, over 1 plus h nu kBT plus 1. That's right. Minus 1 squared. Okay, so this plus 1 and this minus 1 cancel each other out. You now have this over itself. So that gives you 3r So this part down here is going to cancel that part there. So that gives you 3r1 plus kBT over h nu. Yeah. Okay. No. Ooh, okay. See, I tell you, I make mistakes fairly frequently.
Was a mistake in the last term?
There is a mistake.
In the last term?
Yeah. It was with my application of the limit.
Did you take a limit already?
No, it's when I applied this. So we're gonna give Caroline a bit of a chance. You've already bumped your score up enough.
I have a question about the way before derivation, like that one term, right? Letter.
It's okay. Look to see how I was applying, going from e to the 1 over x. this into each one of these terms. Hmm?
Should have been flipped. It should be like 1 plus HV over KBT.
Well, we're letting Caroline sort it out. She's got this. Where? Not the bottom one. Top one, right? I flipped this. Right? Because it's the value that was 1 plus is the same as what was in the exponent, and I flipped that one. Right, so, and I done it correctly on the bottom, right, where it's the same as what was in the exponent, but in the top one I flipped it. This is also why on exams you get lots of partial credit for getting stuff right and then just having some mathematical error, because I obviously do the same thing. Okay, so this part here should be h nu over kbt, right? And as t is getting really big, that number is getting really small, and so that approximates to 1, right? So if this term here is bigger than that term, so this term goes away, and you get back 3r, which is where we should be at high temperature. Come on. You guys, you not jazzed by that?
Do we need to know this, like the steps, how we derive or prove that it was 3R?
No.
Or we need to apply 3R, right? Like if you
Yeah.
give us a problem, we need to apply 3R. or
Well, not
equation.
just 3R, but more the low temperature stuff.
Yeah, like, yeah.
Yeah.
Derivation.
But the process of doing, another thing that we're showing is the process of doing the derivation is, what does experimental evidence say for very low values and very high values? And does your equation that you came up with match those? So one of the processes of verifying an equation is looking at the limits. What happens when it goes to 0? What happens when it gets really big? Does what you came up with agree with those two limits? We're going to be using that a lot when we're talking about particles in a box and or solving some parts of Schrodinger's equation. Is, you know, these are the limits. It has to agree at these 2 points. We can toss any equation that doesn't meet those criteria, right? Okay. We will, let me give the more correct form of Einstein's heat capacity. I think it's in your textbook, but the form, a lot of times they make things look a lot more clean and nice. So we're going to say let phi E be h nu kBT. This is actually called Einstein's temperature. This symbol here, they call it Einstein's temperature. Heat capacity is equal to 3RF, where F is equal to Einstein's temperature squared over T E Okay. So now the key, one of the flaws in Einstein's derivation, and I unfortunately erased it. Oh, no, it's still here. Is we're assuming a single frequency. So with what Einstein said is that as these molecules fluctuate about, they can only do so at a particular frequency, and that the frequency for every single atom is the same frequency. It really simplifies the math, right? That is, well, clear up the part. So the blue line, or the circles here, are the experimental results. Red line is Einstein, and then next time we're going to talk about Debye. He made a slight adjustment, which essentially was saying, why do the frequencies of vibration all have to be the same? So I'm just going to show you the expression. We're not going to do the derivation because the integral actually has to be done using a computer. And it's something that we can't actually take the integral of. So Debye was the one that took Einstein's idea and just said, we can use any frequency, and you can see that it then fits the data perfectly. Einstein was fairly close, but he had oversimplified the matter by saying all the frequencies were the same. Okay. So there we go. We'll pick up there next time.